Today I'm going to do a review and tear down of this 9-volt lithium-ion rechargeable battery. For this battery there are two different kinds. One with a USB port, usually on the side so you can plug in and charge the battery. One without a USB port. And this one is without a USB port, so you're going to need a dedicated charger to charge the battery. And because I don't have a charger, I can use another brand new alkaline battery and just plug it right in, just like that. Well, I was expecting an explosion or something spectacular, but nothing happens. This is so anticlimactic. Please don't try this at home. You're essentially connecting two batteries in series and short them out. I'll explain to you later in the video why it's not the end of the world when you short out this battery. The first thing that strikes me is the weight. It feels like it's a lot lighter than a regular 9-volt alkaline battery. So let's put it on the scale and see what's the difference. 27 grams versus 45 grams, 46 grams. So it's almost half the weight compared to a regular alkaline battery. What a difference. The physical size is exactly the same, but wow, it weighs a lot less. It's time to do a teardown and see what's inside. It looks like it's completely sealed on the bottom, so I'm gonna have to open it up from the top. Whoa! Haha! So here is the inside of the battery. We got two pouch cells connected in series. We got a circuit board that is surface mount on one side only. The other side is for the battery terminals to be spot welded onto the board. These are just regular lithium-ion pouch cell batteries, and the dimensions of the cells are 3.5 centimeter long, 2 centimeter wide, and 6 millimeter thick. Let's take a look at the board here. We got two main chips on this board. The one on the left is 8205A. This small chip here on the right side labeled U1 is actually a DW01. It's usually used in conjunction with the 8205A chip for lithium-ion cell protection. It provides cell overcharge, over discharge, and overcurrent protection. So here are the schematics for both of the chips. So 8200 series on the left here, on the right is the DW01 chip. So this chip is responsible for cell protection. On the DW01 chip, we got over discharge, overcharge, and also overcurrent protection. But because this chip provides very small current protection, we're gonna need another chip to increase the current. That's why we have to use the 8200 series. It has a dual MOSFETs and it has a higher current output. So by combining both of these together, we have the overcharge, over discharge, and overcurrent protection with a higher current protection. The next thing I'm going to do is to check on the capacity of this battery, because it's rated at 600 milliamp hours. So I want to make sure that it is actually 600. Judging by the size, I doubt it's going to be 600. So let's do a discharge test. I'm discharging the battery at 200 milliamps because of the size of this battery. So I'll be back when it's done. Alright, it has been 2 hours and 36 minutes. And the test is done. The total capacity of the battery is 517 milliamp hour, and that's about 86% compared to the advertised capacity. We're close, but not quite there yet. The next test I want to try is the test on the overcharge, over discharge, and overcurrent protection. So let's go over the overcharge protection. So how do we charge these batteries? The best way to charge this battery is to use a adjustable power supply, because this battery is real small, so you're gonna need to have a much lower current to charge it. So with an adjustable power supply, you can adjust the current down to very low level. This particular battery is 600 milliamp hour capacity. The optimum charging rate is about 1/3 of capacity, or 0.2 amp. I do not have anything 0.2 amps, and using an adjustable power supply is really a pain to set up every time I need to charge this battery. So I'm going to use power bricks to charge these. The problem is this one here is rated at 4 amps. This one here, 1 amp, which is way more than the charging rate recommended for this battery. Let me show you what happens when I plug in these 9-volt power supplies to charge this battery. The first one is a 9-volt 2 amp power supply. I've got my amp meter and my volt meter ready. This is just measuring this cell on the left, but the cell on the right should be at the same voltage. So the battery starts at 3.8 volts. Watch what happens when I plug this in. 2.5 amps, and the battery shorts up to 4.4 volts. That's a lot higher than 4.2 volts. Just a few seconds later, the controller recognizes that the battery is being overcharged. So you can see it starts to turn on and off. And you can also see here the battery voltage goes up to 4.4, then goes back down to 4.0, up to 4.4, back down to 4.0. And over here the current starts to go up to 2.6 and then goes back to 0. So it turns on and off to limit the charging currents. So using a high current charger like this does not work for this battery. So next, let's try it on a 9-volt 1 amp adapter and see what we got. Here we go. That's pretty cool. Exactly 1 amp. 4.19, 4.2. Alright, it's been about a few minutes, and here's what's happening. It charges the battery up to 4.25 volts for a few seconds. And then it turns down to 0 amp. The battery voltage goes down, and then it turns back on up again. And because the charging current is 1 amp, which is much lower than the previous charger, right, over 2 amps, the turning on and off cycle is a little bit longer, but it still turns on and off. So the charging process is not very efficient. It's going to take a while. So for this charger, if I want to use it more efficiently, I'm going to have to connect more batteries in parallel. So right now I have 3 batteries connected in parallel, and they are being charged by the 9-volt 1 amp charger. Let's see how the current is divided among the 3 batteries. So the first one is this one. We got 0.3 amps on this one. The second one is this one right here. We got 0.6 amp, 0.6 amps on this one. And the last one is this one right here. And we got 0.3 amps on this one. They're not exactly distributed evenly, and that's because this battery here is more discharged than the other 2. But by connecting 3 batteries in parallel for a high current charger, it makes the charging process a lot more efficient. Alright, it has been about 2 hours and the battery is full. You see the battery voltage now is 9 volts. This is not actually the voltage of the battery, because the system is still plugged in and my charger is 9 volts. So that's the voltage of the charger. Let me show you what happens when I unplug the charger. So here is the plug to my 9 volt charger. Unplug. And the battery voltage goes down to 8 volts. So this is actually the voltage of the 3 batteries. Let me plug back in the charger and show you what happens when the battery is fully charged. And let's measure the current going to this battery here. We got 0 amp. This wire goes to this battery here and is 0 amp. And finally this wire goes to this battery here and it's 0 amp. So when the batteries are full, the BMS actually cuts off power going to the battery. So that is pretty good. My next test is the over discharge protection. So previously I did a discharge on one of the cell and the voltage of the cell goes down to 2.8 volts, right, when it was under load, and now it rises back up to 3.48 volts. But the battery is actually down to almost 0, right? It's a full discharge. The other cell is still about 3.8 volts, which is about 60 to 70%. Now let's check on the main output on the main terminal. This is coming out of the controller board. 7.3 volts. I have my car headlight here, and let me show you what happens when I hooked up the car headlight to the battery. The headlight does not turn on and the battery voltage goes down to 0. That means the controller board shuts off the output to the headlight. That's because it is over discharge, and that's because this cell right here is way too low and the controller can sense it and shuts down the output. Let's see what happens when I disconnect the load. Goes back to 7.3 volts. So the over discharge protection works beautifully. For the overcurrent and short circuit protection, I'm going to have to charge the battery back up to normal voltage before I can do the test. I charged the battery up to 7.6 volt right now, and that's 3.8 volts for each cell. Let's see if it works. I got my car headlight here. So the headlight does not turn on and the voltage goes down to 0. So the overcurrent protection is still on. Now let's try on something else that uses less power. I got these LEDs here that runs on between 3 to 4 volts each. So if I put 2 in series, it will be about between 7 to 8 volts, which is perfect for this battery. So here we go. Alright, there we go. It's using about 0.7 amps. And the battery goes down to 7 volts. But it's working. The overcurrent protection does not kick in, and that's because the LED uses much less current than the car headlight. The car headlight uses about 4 amps, and that's too much for this battery, and that's why the overcurrent protection kicks in when I hook up the car headlights. Now what if I completely short out the main 9 volt terminal that comes out of the main controller? What is going to happen? There's only one way to find out. Are you ready? Boom. You see the voltage goes down to 0. The current is also 0. And if I remove, the voltage goes back to 7.6 volt. So the overcurrent and short circuit protection is also working. If I have to compare this battery versus the one that has a USB port on the side so you can plug in a 5 volt USB to charge the battery, I prefer this better, mainly because of the price. I bought 4 of these for $12, and that's about $3 each. The other kind of 9 volt battery with the 5 volt USB port on the side, those are about between $9 to $11. So it's about 2 to 3 times more expensive than this. The capacity between this battery and the one with the USB port on the side are roughly the same. It's just the difference in price. The disadvantage of these batteries is that you need a separate 9-volt charger that has a low current enough to charge them, about 0.2 amp to be exact, to charge each battery, or you have to charge them in parallel at the same time. That means they need to have the same state of charge and the same voltage before you plug them on parallel to charge them. There is one significant difference between the 9-volt lithium-ion with USB and without the USB port. The one with USB port, it uses a single lithium-ion cell, and because it's only 4 volts, so it uses a boost converter to boost it up to 9 volts. The battery will start at 9 volts and it will stay constant all the way until the end, and poof, goes down to 0 without any warning. The one without the USB port, it uses 2 cells in series, and therefore it doesn't start at 9 volts. It starts at a low voltage, and in this case around 8.2 volts. The voltage will gradually go down, but it doesn't go all the way to 0 volts. It only goes down to 6 volts when the battery is completely empty. Most 9-volt devices won't have a problem operating under 9 volts. But if you have something that is sensitive to 9 volts, then this is something that you have to consider. And that's everything you need to know about 9-volt lithium-ion rechargeable batteries. That's all I have for now, folks. Thanks for watching, and I will see you in the next video.